Hi, and welcome to Engineering Tech Tutor, the online resource for student and professional engineers. In this episode, we look at simple stress and strain. So let's do some of the basics before we begin. If I take a material and I apply a load, pulling the material apart, that is known as a tensile load. Inversely, if I reverse the forces, so they're compressing the material, that's known as a compressive load. It's worthwhile to memorize these two words because we will use them throughout the presentation, and they're also used generally in engineering anyway, so it also makes sense to know those. Okay, so what is stress? Well, stress is a way of describing the pressure a material is subjected to when a force is applied. If I look at the example here, we have a compressive force, and it's being applied onto the circular surface, which is shown with the arrow there pointing from area A. When a force is applied to an area, it generates a pressure, but as engineers we also refer to that as stress. The symbol for stress is sigma, which is the orange symbol, and stress is measured in pascals, although quite often when we're writing this down we will just use the abbreviation of PA. 1 pascal is 1 Newton per square metre, and quite often when you're given an example to work through, the dimensions of the component you'll be given will be in millimetres or even maybe centimetres. Also be careful to make sure you convert it into square meters. If you do the calculation with square millimeters or square centimeters, you will be a factor out, and you may not necessarily notice you've done that. The equation for stress is force over area, and again with force also be careful to make sure you only use newtons and no other unit, otherwise again you'll have problems when you run the equation. Right, so let's do an example. So in this example, I've got a compressive force of 1 kilonewton, which is 1,000 newtons, and it's applied to a bar with a 50 millimeter diameter. What is the stress in the material? Okay, let's work this through. So we know that area of a circle is pi r squared. We know we need to be doing this calculation in meters, not millimeters, and we also see we've got the diameter and not the radius, so we can quickly work that one through. 50 millimeters is 0.05 meters. If I divide by 2, I get the radius. I can then square it and multiply by pi, as shown in the first line of the equation there. And I'm then given the answer of 0.001963 meters squared. If I then take the stress equation from the previous slide, I take my force of 1,000 newtons and I divide it by my area. I'm then given the answer of 509,424 pascals. That's quite an ugly way of writing down the answer. It's not normally typical in engineering to write it down in this way because well, it's quite an unwieldy number. What's quite typical is we would then convert this into megapascals, which is 1 million pascals, and that gives us a slightly easier to write answer of 0.509 megapascals. Okay, so what is strain? Well, let's move now into a tensile example. So if I apply a tensile load to a material, it will increase in length, it will stretch or elongate. You may not see it, but it will be happening, even at a very small level. Strain is a way of describing how much stretch you get in the material. Is effectively the change of length in relation to its original length. The symbol for strain is epsilon, or the orange symbol there. And because it's a ratio of lengths, it is dimensionless. It'll have meters, and I divide by meters, the meters term cancel out, so I end up with no units at all. Strain then is the change of length, delta length, also shown over the triangle, over length. So it's not the total length, the total stretch length, it's only the change in length. So be careful just to make a note of that, as shown in the diagram on the left hand side there. So can I calculate strain? Well, yes, there is an equation for it. I've just shown it to you. However, in practical terms, unless you know how much your material has stretched by, you can't calculate the strain. So we do need to first talk about a thing called Hooke's law. Once we've talked about that and you understand how to use it, then we can then calculate how much strain there is in the material. Okay, so what is Hooke's law? So on the previous slide we said that if we apply a tensile load to a material, it will stretch. And so it stands to reason that if I keep increasing that tensile load, that the amount of stretch I get in the material will increase and increase. To begin with, and we won't talk about what happens afterwards, but to begin with, the link between stress and strain, or stretch and load, are proportional. the law of proportionality, as is known, is effectively the basics of Hooke's law. That relationship will continue until you reach a point called the limit of proportionality, beyond which you start to get plastic deformation in the material, which is something we'll come on to in a later episode. But if we concentrate today just on the orange line, where stress and strain are proportional, then it allows us to then calculate strain in the material. The proportional relationship, as I said, is known as Hooke's law, and it only applies to the orange section. Hooke's law does not apply beyond that. The relationship between stress and strain is known as the tensile modulus. It's also known as the Young's modulus. It's given the symbol of E. The modulus, be it tensile or Young's, is measured in pascals. So modulus E is stress over strain. So stress has the units of pascals, strain has no units, and so the outcome is you have modulus with the same units as the stress. So let's try and do an example. Okay, so in this example we have a tensile load of 10 kilonewtons and it's applied to a bar with a 50 millimeter diameter. The material has a Young's modulus of 65 gigapascals. By how much does it stretch? Well, by asking how much does it stretch, what we're actually asking is how much strain is there in the material. Now, to get to that answer, we have to do a few calculations first. The first one is we need to calculate the area that the force is applied to. So we know that area of a circle is pi r squared. We need to do this calculation in meters. We've got the diameter in millimeters, but that's not a problem. We convert 50 millimeters into 0.05 meters. We divide by 2 to get to the radius, square it, multiply it by pi, and we come out with the answer of 0.001963 meters squared. Good. Okay, let's move now on to the stress. So we have force and we have area. We know the force is 10 kilonewtons or 10,000 newtons. Again, we're careful to make sure we use newtons in the calculation and not kilonewtons. And we divide by the area we just calculated, and that gives us 5,094,243 pascals, or to put it a slightly simpler way, 5 megapascals. But I'm not going to convert it now into megapascals because we're going to use it in a minute in pascals. I don't want to mix up the units, otherwise we'll fall foul of an error. Okay, so we know that modulus equals stress over strain. We know stress, we know modulus, we don't know strain, so we're going to have to transpose this formula. It's only got 3 elements to it, so it's not going to be difficult to do. First of all, let's put the numbers in we do know, just to make it quick for us. So we know modulus is 65 gigapascals. Just for the sake of the amount of room it takes up, we'll leave it like that for the moment. We've got the answer of 5 megapascals for the stress, and it's the strain we want to know. If we move on to the third line, we can transpose that. So we move the modulus under the stress and move the strain onto the other side of the equal sign. That then gives us the equation of strain equals stress over modulus. At this point we can then expand out the gigapascals into pascals, noting just how many zeros there are in doing so. So now we have 5 million pascals divided by 65 billion pascals. And that gives us a strain of 7.837 times 10 to the minus 5 meters. That's not very usual or a very common unit to use. So what we'll do is we'll convert that into a much more sensible use of microns or micrometers, and it works out at 78.37 microns. Great, hope you got the same answer. Well, that's the basics of stress and strain. In future episodes, we'll look at shear stress and shear strain and what happens when you go beyond the limit of proportionality on the stress-strain curve. Until then, thanks for watching, and please do subscribe to our channel. Thanks very much. Bye-bye.